my third lecture, okay, in the last one. And the thing is, for this last lecture, actually, I want to take just one step back, because in my last lecture, I actually felt the need to introduce the idea of Bell inequalities, okay, because I use it. So Bell inequalities is very important to characterize entanglement in many different systems. And I started to use, then I realized, okay, I didn't properly introduce the Bell inequalities. And so Stephen's talk already helped, because he already introduced many of the concepts that I'm going to use. But I think it's more or less straightforward, so I can explain quickly with a couple of slides, and then we move back to the quantum networks. Okay, so to discuss this Bell inequality, you have to think about a source of photons that emits, for example, 2 photons. I'll use this notation of this book here, in case you want to read more. And so you just send 2 photons that I'm called here E1 and E2, and these 2 photons go through to this analyzer, which is a polarizer, and the results for this polarizer you just encode as +1 or -1. So your vertical output in the beams in your polarizer is +1, the horizontal output is like -1. Okay, and then you have some rotation angle for your polarizer that I put here as A, and for the polarized 2 as B. Okay, and let's consider our local realistic theory, and in the sense that I will call this lambda a set of parameters describing the system, but a full set. And these parameters, they can be both null or unknown. Okay, I don't really need to specify if I know all parameters. And I have some probability density for the system to be described by lambda. So there is a bunch of parameters, and there is some density probability of having this exactly set of parameters in your system. And then now I write this function A lambda A here. This function just provides the results +1 or -1 of the measurements in one of the polarizers. Look, this number can only be +1 or -1, so the modulo is always 1. And it's going to be a function of lambda, so it depends on the set of parameters, and depends on the position of the polarizer A, okay? And the same goes for B lambda B, okay? And so we can consider a situation with equal probability of having +1 and -1, so this is very common. And in this situation, if you have equal probability, when I average, okay, over all measurements in the possibilities of measurements A or in polarized 2 with B, the average should go to 0. And then I can start define these correlation functions, okay, between measurements in the first polarizer with angle A and the second polarizer with angle B. And this correlation function will look like this. So you have an average of this is a usual definition of any correlation function, normalized correlation function. So you have the product of the 2 results, an average of this product, minus the product of the averages, divided by these normalization factors. Look like the modulus of this normalized factor is 1, okay, because just your measurement is just +1 or -1. And then we have this average here to be 0. That's what we chose, this kind of, we tuned the system to be like this. And so you get this more simple case where your correlation function is just the average of the product of the 2 measurements, which you can write like this as you have the probability density of having this set of parameters. Okay, and then let's define, it's a little bit, okay. Let's define this quantity here, small s, okay, with this, that depends on the set of parameters of your system, and depends on 2 different positions of polarizer I, and 2 different positions of polarized 2, 1 and polarized 2. And this quantity is like this. So it's just the product of A and B, but for different polarization angles, okay? Okay, and I can rewrite this like this. You have this A multiplying a subtraction of two different B's, or A multiplying the sum of two different B's. And that's the point. B can only be +1 or -1. So if one of the B's is +1 and the other is -1, then this will be 0, okay? And if this one is +1 and -1, sorry, this one will be 2 or -2, and this one will be 0, or vice versa, okay? And A can only be plus or -1, and then it's easy to show that this can only be +2 or -2, okay? But I'm not interested exactly in what's the one measurement of this quantity, but actually what's the average of this quantity. I don't know what are this set of parameters lambda, but I know that this can only be -1 or +1. So when I have the average here, you have a number that's going to be between -2 and +2. And then you define this as being big S, and you see that this quantity here, then you show that this can only be, if you follow the conditions for this measurement, this can only be a number between -2 and +2. Okay, and so that's the Bell inequality that we use for polarization. That's called CHSH inequality. And that's the whole deduction. So there's no quantum mechanics here, okay? I just assume some, more or less, some reasonable conditions for the measurement. Okay, but then let's see what happens with a photon, okay? And so I have some direction of propagation for a photon with a polarization that can be perpendicular to the direction of propagation. Let's see if it's, well, it's not, okay. So you have xy is the plane of polarization, and z is the direction of propagation. Then I can use a basis. I can describe the polarization of the photon in a base, x and y, with x being this column vector 1, 0, and y being 0, 1. And in general, the polarization measurement, that polarizer I, so it will have a direction that's indicated by U, and you come with the individual photon, and then the result +1 or -1 come from this operator here, okay? So if you are in X polarization, you're going to be +1, Y polarization is going to be -1, on this basis that is aligned with the X vector, okay? But you can actually put some angle, and you can have some theta, and then you can just rotate your polarizer. And actually, your detector will detect this other function that will depend on your angle of your polarizer. And now the results plus and minus will be related with these different eigenvectors, okay? So you have some algebra of your polarizers and the state of the photon. And now you have this basis that's a general base to describe a two-photon system. So you can have a polarization, any polarization for the first photon and the second photon. And with this base, you can describe any two-photon system in polarization. And now, but now you want to calculate some probabilities. For example, let's say I have a probability of measuring +1 and +1, both with polarizer 1 and polarizer 2. And now, quantum mechanically, I will indicate that by projecting the state of the photon into the eigenstates, okay, for this rotation with angle A or angle B, okay? And so on. I have something similar for detecting plus and minus, or for detecting minus and minus, okay? And also I can have probabilities to detect singles, okay? To detect singles, all the probability to detect a plus measurement with an angle A is just the sum of the coincidence of detecting plus plus and plus minus. So these are all possible measurements with the angle B. When I sum all possible measurements in B, I have the total probability of get the measurement, a certain measurement in A. Okay, and in this language, AA is just the measurement result, which is +1 or -1. BB is the same for the other detector. And then I can describe these correlation functions the same way. okay? Very similar, is the same way as the previous one. As I mentioned, this is just a general definition for correlation function between two measurements. And I can have the same conditions. I mean, the average of these quantities, +1 and -1, can be +1 and -1. You can make these actually close to zeros just to balance your detector. Let's see if I can move forward. Okay, but when I when I do, let's move back a little bit. Okay, when I do the average of this multiplication here, so you saw right, here's the same way. I mean, the modulus here is +1 is 1. So here's just 1 in the denominator. This we can consider 0. And then we are left with this average of the two multiplications. See that this average is like this. If you have +1 times +1, so you have +1 here, multiplied by the probability of getting this +1, +1. If you have minus the minus, you have -1 times -1 times the probability to get it. And when you have +1 and -1, see the multiplication of +1 and -1 will give a minus here. And then you have to multiply for probability of having that, and the same here. Okay. So let's say that we have this state. You can construct this kind of state. That's what we've been called attention that this is an entangled state. And then we've calculated this probability plus for a certain angle AB connected with this angle theta A and theta B for your polarizer. Then you get this result. That's the same with P minus minus. And then plus minus will get this other result here. And you can manage to have the situation of all the single probabilities being half. Okay, so you end up with these conditions. And then once you calculate these correlation functions, you have these results for the correlation function. And from here, you can actually choose some angles, okay, for here that will result, let's see if it reacts, that will result in this S as being larger than 2, okay? So this violates that very reasonable condition that we got in the previous slides. And the trick is, okay, so this is the violation of the Bell inequality that comes from quantum mechanics. And the trick is that this cannot be described by this. So what's the mistake, let's say, is the reasonable assumption that the measurements in site A do not depend on B. You see, quantum mechanically, A, the detection in a site A, will depend not only of A, but also on A and B. But if you assume something reasonable, which means that your detector result only depends on your local choice for your polarizer, if you assume that, then you end up in a situation that is violated by quantum mechanics. Okay? So that's a very useful result for us for many different things because it really helps us to capture a more quantum nature of states like this, okay? And that's what we are going to use over and over to characterize many of the systems. This is called an entanglement witness. It's not an entanglement quantifier. Usually when you do tomography, when you have for example, you characterize the density matrix of a state, you can generate some measure, some quantification of the entanglement. So you can more or less have an idea of how many qubits you can use to create that state. And once you have this idea, you say, okay, I can use this state to do some kind of protocols, okay? But entanglement witness usually is to tell you that you have or you don't have entanglement, okay? However, you do have nowadays many practical applications of this quantity. So one particularly important result was in the beginning of, I think, 1993. There was a protocol for quantum cryptography by Eckert, in which he showed that you can do quantum cryptography with this kind of states, and it would give the same result as other known protocols. And the interesting thing that in the article by Eckert, if you want to ensure the security of your cryptograph protocol, you just need to see if you violate the Bell inequality. So Bell inequality, even though it doesn't have to do anything with quantum mechanics, it was introduced more for philosophical reasons. But with Eckert's work, it becomes a measure of security of a network. Okay, so that's usually a very good number to have because it guarantees a lot of what you can do with the output with your end states in the system. Okay, so I already discussed this in the my last lecture, but just passing through, just to call attention. Actually, Stephen also discussed how you build this kind of entangled states. It's just to call attention. I mean, for this kind of Sagnac interferometer, you just have these two different ways to circulate the Sagnac, which would result in one polarization or the other. And then if you excite the Sagnac with a 45-degree polarization in the pump, you have the two situations simultaneously, and then you end up with this kind of, effectively, with this kind of states. And so that's, okay, what you get after you do that kind of excitation with your pumping beam at 45 degree. Okay, you have here the two situations, I mean, circulating in one direction or the other. And when you actually is going to measure these Bell inequalities, that's what you get. For example, if you have coincidence in one polarizing vertical polarization in polarized one, and horizontal polarization in polarized one and vertical polarization polarized two, and then you are actually just change the degree, the rotation in, I mean, here is kind of hard to read, but this should be theta 2, and this is theta 1. So you put one polarizer with some angles, and the other polarizer you just scan. And you see, if you don't align well the Sagnac, if you have the H and V basis, this is just the trivial result. You get always very good fringes. But then when you rotate, you don't see, your system is really dependent on the way you put a polarizer. So you just get a lot of not a good information. But when you align well the Sagnac, then if you just rotate the angle theta 1, the system looks exactly the same. I mean, it really follows through. It's like it's indistinguishable. It is run through one side or the other. You can't really notice the difference when you rotate the angle. That's the situation where you're going to violate this Bell inequality, okay? That's operational would be read like this. And in this case specifically, we are talking about a Bell inequality of 2.48. It's not even maximally entangled, but it's already with some good visibility. Okay, so we can go back to the quantum networks. And now, in my last lecture, I stopped when I discussed the entanglement between two distant ensembles. And I just comment that actually the protocol for long-distance quantum communication was not about extend the entanglement between two ensembles, but actually extend the entanglement between two chains of ensembles, okay? And the reason, I think, it will be more clear after I explain. So what we have now, consider that you have now these two magneto-optical traps, one in one optical table that I call site L, and the other in another optical table that I call site R. They are separated by around 3 meters. And then I can do the protocol from my last lecture to entangle these two memories, and now I have memory, okay? So I can hold this entangled pair and wait until this second pair is entangled. When the two pairs are entangled in parallel, then I can read everybody together, and then they're going to emit photons, and then I'm going to, this entanglement between the memories will be mapped, entanglement between these modes that are being emitted in the reading process. And looks that for this kind of system, the same way as we synchronize two memories, it's really crucial to have memory here because you gain a factor of 30 in the efficiency to generate this whole state, okay? And then what you do from here is that actually, remember that in the last, my last lecture, that state that we create is just 0, 1 plus 1, 0, is in the number base. I'm not specifying the polarization. So I can create a state in the number base, but in the number base in vertical polarization, or in the number base in the horizontal polarization. Now in the up pair or in the down pair. And then I can combine them in a beam splitter and pass these two fields to analyze. So what we're going to have after these beam splitters here, effectively, if you condition detect one click here and one click here, you are going to have effectively this state, this entangled state. Okay, that's the magic here. Okay, and notes that what's interesting here is that you have basically a product of the process that I described in the last lecture, in which you generate a state that depends on this phase here that I call attention that is tricky to control. But actually, this process here after the beam splitter only depends on the difference in the phases. And that's typically much more well-behaved than just a single phase that is free to move, okay? So this state can actually be used to perform quantum Fourier distribution, okay? And that was the idea, actually, from the original DLCZ protocol. Just to be a little bit more specific, why is this interesting? I mean, if explain like this, like in a hand wave, it's not as clear. You have to look at oops, sorry. I have to go back a little bit. So what we showed here in this article is that you can violate Bell inequality here, here, and here. So you remember that in the last lecture, I showed a certain state that's 1, 0 plus 0, 1, and I had to do a tomography of that state and then calculate the concurrence, and then we got something like 10 to the minus 3 for the concurrence. It's above 0, it was entangled. Now I use 2 of these states, okay? And then I combine them, and then I violate a Bell inequality nearly maximally, okay? So this is just to give an idea. I already called the attention. The number -3 is just meaning that you have a lot of vacuum. But this state is conditioned on have a detection here and here. So you do pause selection, and you throw away the vacuum. Once you throw away the vacuum, then you get a state that's close to this. This state should violate maximally the Bell inequality. And that's why you get such a good violation of the Bell inequality. So, but the experimental setup is something like this, okay? And what is interesting here, you see that this is a magneto-optical trap in which we excite 2 different cylinders, but you see that the right field propagates through the same fiber, and we just split the light from the 2 ensembles with a beam displacer very close to the vacuum chamber, and then we put it together again right after, and then the 2 goes to different fibers, but they have opposite polarizations. And the same goes for the reed fields. The interesting here is that you actually have 2 channels, and you propagate both the right field and the photons through the same optical channels with minimal difference between them. This is very robust. So basically, we had almost 1 night of passive stabilization here. And more, I mean, these compensators here, actually, you can compensate the difference between the two channels. You can actually choose the phase difference. You can choose to put there pi over 2, whatever, okay? So it's actually, you not only fix it, you choose the value of the difference in the phase, okay? And so this is the kind of idea that is all the DLCZ protocol, all operations should be like this. You should have always 2 chains in which the difference between the 2 chains are 2 polarizations. The channels are just 2 polarizations of the same single mode fiber. Okay. So just switching gears a little bit. Oops. Okay. So if you want to scale up the system, so these are all like almost 20 years old experiments. the problem is it's really challenging to scale up from here. So this is an idea on how, in principle, you could do, I mean, a quantum repeater. Let's start with these small circles here are just atomic ensembles. They are together here because they are in the same site. And these diamonds here are just control stations that send pulses that would control to do the entanglement swapping, for example. And these are the entangled pairs. So this is just an idea on how you can scale up. So you start with generate entanglement in single sites. So that first step of generate entanglement you can do very efficiently locally. So you don't want to do anything that's inefficiently between distant sites, okay? Because if you have distant sites, just the light traveling from one place to the other, a few kilometers is milliseconds, okay? And then you don't want to add milliseconds with 10 to the minus 4 probability. So the really, I mean, not efficient part you put just locally, and you do the swapping, which has a high probability, around 50%. You do the swapping for the long distance, okay? And that's how you can start with a local entanglement, and then you do a first swapping to expand the entanglement, and then you can do a series of swappings just to increase. And then, so this is the order of swapping: 0 order, first order, second order, third order. And so the swap operation, I think it was already realized since then. We did some preliminary results in 2007, but we were not successful. And what happens is that when you go down this stream of operations, you need pure and pure states. So your P, the probability of success, that one that generates the state, needs to go down, okay, and it gets less likely to succeed. And in order to work with less likely state to succeed, you need higher memories. You need more memory time. So the coin is always memory time. So with 20 microseconds, we could not do that. Probably with 3 milliseconds, 6 milliseconds, it would be doable to move forward, but we didn't do that. And actually, I don't think nobody ever got to, for example, to a 2 up to now. But one thing that we did in the sequence of this is to analyze the following. I mean, one thing that is tricky is that as you go, you increase the number of steps of your number of swappings, you need to have more pure states. And then we did some analysis on this protocol, on this kind of system, in which we analyzed, for example, the Bell inequality violation of the concurrence. And then as a function of P, this is for a theoretical analysis with some more realistic conditions that we learned when we developed the experiments. And then we consider a different set of swapping. So this is for the first swap. You see you have a lot of, you violate well the Bell inequality. But then as you increase the swappings, you start to be more stringent. You need the P to be smaller and smaller, so you need more and more pure states. And the same for the concurrence. And you can actually build some diagrams like this, in which you see this P is the amount of the small probability that you have to generate the state. And H0 is the same, more or less the same meaning, it's just the suppression of 2 photon component. But it gives more or less the same result, which means that this is a line that you can violate this curve here. You can get a concurrence, say that you have a non-classical state. And this other, the blue curve here, it's the limit where you can violate a Bell inequality. So these are different measures. One is just concurrence, and other the Bell inequality. Once you violate the Bell inequality, then these are useful for cryptography, for example. So you have these 2 different bounds. And okay. And then with that, we can get this bound here to see the maximum P that we can use to move forward in the number of swappings. And then you see this increasing time. This is the memory time that's necessary to succeed. And basically, we show that even if you consider all these imperfections, you still have the same scaling as the usual DLCZ protocol, which is actually hard, okay? Because it's not exponential, but it's super polynomial, which is basically it's more than polynomial, but it's less than exponential. But it's still hard. You have to have in mind that DLCZ is like a first generation generation of quantum repeater protocol. I'll come back to that in the end. There are many protocols that were developed after that. Typically, you have to move to more complex hardware, like you do multiplexing. Instead of use just 2 ensembles, you're going to use 5, 10 different ensembles to do some kind of error corrections on the pathway. So it's harder to do with 2 or 4 nodes, but when you start to increase with n, then it gets much more efficient, okay? But the DLCZ was one of the first protocols, so the scaling of the protocol is not particularly good, okay? But it doesn't get worse once you put a lot of realistic imperfections that were discovered during the experiments, okay? So just to highlight some of the first experiments that we did in Recife. So I did a lot of work for these old works in 2007 and 2005. I did at Caltech in a postdoc. But in Recife, we also set up like this. I already showed some results from Recife in my last lecture. But these works that I'm going to show now are preliminary to that one. But just to give an idea, so this is a usual optical table for a cold atom system. So some of you probably work with cold atoms, others don't, but at least heard a lot of cold atoms here. And in the heart, of course, is always a trap here. And in this case, we need to have something that's as stable as possible. So here's a first generation of fiber optic-based atom trap. We are actually improving that recently. And this is just a, let's see if I can pass forward. This is just an image of our MOT. So, oops. And these are some results that we got, I mean, right for the quantum regime in our system, so we can have a G12 up to 30. We didn't optimize a lot. We just want to make it work. And then with this R factor that should be above 1, for the classical limit, you can get more than 100 here. This is the quantity that I discussed in the last lecture, these cross-correlation functions and the autocorrelation functions in each of the fields. And this is the probability to detect the field, a photon in field 1. Let's try to move a little bit. And this is the probability to extract the photon, okay? To detect the photon once you prepare the state. So this one was a first. So the thing is that every time I put a new system to work, it is always a good opportunity to learn a little bit, to do some calibration, and then in the calibration to do characterization and do some theory. And so for this kind of system, once we put it to work, we did some theory from first principles to try to model this kind of memory in a more detailed way. So if we have this system here, 3-level atoms, once you detect a click in the first photon, and then you prepare some collective state that I showed in the last class that it was just a Dix state. Okay? But a Dix state actually is a very idealized way to actually represent the state. Because the actual state, you have an amplitude here that will depend, for example, the position of the atom in the ensemble. And then you have some phase here that come from the phase of the excitation fields and of the emitted photons and the position of the atom in the ensemble. Okay? And actually, so you have some phase grid, and then you have the one atom in S, all the others are in G, and you have no photons after the first photon is detected. So the grating has more details. And for the temporal evolution, you see you have a free Hamiltonian with atoms and fields, and then you have the interaction with the read field, because now I just want to model the reading process. And then you have interaction with vacuum modes in this transition and these transitions. In the vacuum modes, I will treat it, I will do a first principle treatment of it. When I do this, then I have this evolution in the reading process, in the extraction of the second photon as a general evolution. You see that since I have spontaneous emission, then I can emit the photon in any direction, okay? And so I have one atom, for example, here. So all atoms are in G and have +1 photons. This means one atom is in S, and I have one photon, because this is just a transition that I go up, and then I emit a photon here. And from this, I can deduce the wave packet of the read field, of the read out photon. Some interesting things appear when you do this kind of first principles theory. Let's see if I can, okay, let's go there. Okay, so this is a paper that we published after the first one that was a theory. So when you do this, we can actually measure the wave packet, because we can measure the probability to extract the second photon as a function of time. And this, the scatters, the circles are just the experimental results. And the line here is just coming from the theory. When you have here this dashed line, this is just the unconditioned clicks, okay? And one interesting thing that appears, first of all, you have a lot of Rabi oscillations, okay? That comes from the strong read field that we are using. But you also have this, you see the exponential here. This gamma here is the spontaneous decay, but it's multiplied by chi. This chi is actually a super radiant factor. So actually, if you do any treatment from first principle in the system, as it should be with any Dix state, you have super radiant enhancement. And then if you change the number of atoms, you see here the optical depth is just the number of atoms changing. Then you can extract more the photon from the ensemble, and you see that it also accelerates. So the key is the acceleration factor for superradiance. And so that's what's called single photon superradiance. Superradiance was already included. I mean, this was part of the argument for the DLCZ protocol. It was just not characterized in terms of what's the consequence. Because the DLCZ protocol was discussed in a very abstract way, just in the number basis. But if you try to really measure like wave packets and things in more detail, then this kind of effect will show up more directly. But this is like a minimum superradiance, because you just have the first step, preparing a superradiant, a collective state, and the next step is reading it. So it's like a superradiant cascade with just 2 steps. Okay. Oh, sorry. Here? Okay. No, not anyone, not one very specifically. We really have to control the system well. So you can see it better if you do something that's more single mode. So for example, this is actually the experimental configuration. I mean, you have this cylinder, that's the mode that we observe, okay, in the detectors, come from this fiber. But the excitation fields are much broader, so you have plane waves. And so this preparates an ensemble that's quite smoothly. So it's really more uniform in terms of the global phase. This helps to observe this superradiance. But actually, every time that you have some collective state in the system, you get superradiance. It's more natural than we are used to think, let's say. And so that's why if you don't do anything, I mean, it's just a wave packet. But if you do a first principle calculation, you see that the wave packet is accelerated. But we need to do this calculation to see this. You see, that's not experimentally, you won't see just for the shape of the curve. You wouldn't feel that. After that, we are getting used to see, and now we are able to see many other phenomena. For example, after this work with superradiance, we moved actually to measure not in this kind of 3-level system, but we start to measure this 4-wave mix in 2-level system, just Rayleigh scattering. And we were able to see also quantum correlations in this 4-wave mixing. And then it gets more tricky, because if you look in the autocorrelation functions, the autocorrelation function, you find the treatment, that's what I mentioned in the last lecture. You find the treatment in any basic quantum optics book. You have bunching, and the autocorrelation gives 2 for tau equals 0, and the decay gives the spectrum of your system. Okay, so it's really in any textbook, and when you measure, you get what is in the textbook, no problem. But when you measure the quantum correlations, between the two fields, then they are accelerated with key, the same way. Okay, so then you get really the feeling of the collective state. Mm-hmm. But it is common. So that's one thing that is good to have in mind. The DIC work in the 50s, the 1950s, was followed by a lot of polemics, okay? And the thing is that when you do any treatment, okay, of an ensemble of atoms interacting with a laser field and with vacuum from first principles, you get superradiance everywhere. You get a lot of accelerate, you have collective states. And then people look at that, oh, but this is too complicated. Okay, if you do a local theory with a block equation, and then you do propagation, you can explain everything, okay? But then you don't explain a couple of things, like these accelerations, and then you have some semi-classical models, and then you work around some ways. But this DLCZ protocol, I think, is the first protocol that tells how you can use the DIC collective state to do something. And then you have all these experimental results, all in the quantum regime. And then you cannot get any semi-classical correspondence to these results. So in a certain way, I mean, there is just one theory, that's the DIC theory, the full quantum treatment, that explains everything. But all others, they will eventually fail in experiments like this. Okay, but now let's finally enter into the Recife quantum network. As I promised, we would have at least one case study, and that's the case study of what we are setting up there. It's still not fully operational, but it's partially operational, and at least I can explain what we envision, how we are building, and what we envision to do with it. And so we have nowadays this system here. So we already have in place this fiber network. This fiber network is a collaboration between two universities, UFPE and UFRPE. So in the project, so we have a CNPq project for multiplex quantum communication with hybrid quantum networks. The hybrid here is just light and material systems. But then we got money to do the infrastructure inside the universities, connecting different centers, like this is the physics department, and in this center we have the Department of Electronics and Systems. And UFRPE, we have a physics department here that need to be connected from the, so we have a central for informatics service in both universities. And then we connect everything with this center. And these two centers, they are connected by RNP. RNP is a Brazilian agency that manages many of these networks. They have networks in each capital. And there are networks that were, the idea was to use to do any research and more strategic applications. And it was very important also in the beginning of the internet in Brazil, but it is still there. And then we are starting really a good collaboration with them because they have already these fibers connecting different institutions. But we have already like a very good team. We have team both engineering and in the physics departments in both universities. And I'll discuss a little bit more about this team. They are all very engaged in all the research. The original project was more related with telecom problems. So we were planning to use multiplexing with DWDM, to use ultra-broadband photons. But we had to change a little bit. I will discuss later in a couple of slides. But that was the original idea. But we already have this system in place. And actually, for any quantum network, what you need to do in it grows really quickly. So when you have this team here in different sites of the network, actually we have different roles, like you have me, coordinate the project, we have some coordination for each site, but we also have, for example, work with entanglement generation, distribution, many of these people work on this, and then we have people working BB84, quantum key distribution, we have people working continuous variable KKD, people working post-quantum cryptography, some work in polarization control just for the channels, or synchronization of clocks between the sites. these quantum random number generators, and finally, theory also. So you have a lot of different tasks. This actually is a function of the fact that we are an academic network. Okay, so we have multiple interests, and we are a mix of physicists and engineers, and particularly telecommunication engineers. So it's very interesting, for example, to work with different protocols, like entanglement-based protocols, protocols with attenuated lasers, protocols with continuous variables. For example, continuous variables is quite interesting for the telecom engineers because it's connected with coherent communication, the field of coherent communication. And so it's very interesting to have all these protocols. This post-quantum cryptography is very connected with the groups that work with cryptography in general. So they are very engaged on this as well. And you have other different tasks that really require some attention. Of course, these are students that are just professors, postdocs, undergrad students, graduate students, so all of them move in a different velocity, okay? But surprisingly, I think we are moving forward quite well. I mean, this is a very enthusiastic group. And I always say that the quantum network is already working because we are forming so many people on it, okay? So this is already the main product. And for example, in the electronics and systems department, we had last semester, we had already a course on quantum communication just for the engineering students. So actually, this is one of the results is to incubate a group of quantum optics inside the telecom department. And actually to build up the lab here. So we have Ferraz here, for example, that is an expert in SPDC sources, but in this university, he doesn't have much equipment. So this project will also install a lot of equipment there. And so this is just where we were before the quantum network. This is our previous SPDC photon pair source. It's just to call attention to the difference in complexity. We were working with femtosecond lasers that were pumping that SINAC that I explained to you before, okay? And then we'll get some barrier inequality violation to characterize the system. And then we have many master theses and doctorate theses and postdocs and some articles on that. But the system was more like we were really aiming at getting something like that. It was a very good pure state and something that we can synchronize. So these pumped systems are good for synchronization, for example. But then now that we are interested in really using a very simple source that we can distribute in the network. So that's a different approach. So we build really a very simple source with just a blue laser that costs $3, okay? And this crystal costs more than $3, okay? But you just do a single pass on it and no SINAC, and then just use a beam splitter to separate the two fields, and in these two positions here, you can put, for example, some polarizers. So we submit this article for publication, just explain these sources and some characterization and how it fits in the network. And these are just some numbers just to have in mind. So we just have a single pass source with a 0.5 millimeter crystal, and the wavelength of the photon is around 818 nanometers, and the bandwidth is really huge because this crystal is so thin. No? And you see this is the bandwidth of the photon, okay? So there is a lot of different pairs that will give a photon pair inside this spectrum. And actually, if you try, for example, to violate a Cauchy-Schwarz inequality in the system, you see that it depends a lot on your frequency filters. You cannot read here, actually. But the best result, for example, is that you get something is degenerate here in the middle, exactly in the middle of the spectrum, 818 nanometers. If you use a narrow filter of 4 nanometers, then you get the best result. If you enhance the filter a little bit, it goes down. And actually, you can use different filters symmetrically around the pump field. And then you get also some correlation. Cauchy-Schwarz inequality. Look, this Cauchy-Schwarz field you must understand as number correlations. Okay, it's not polarization correlations. But you can also do barrier inequality measurement in the system. As I mentioned, we'll just put a polarizer on one side of the beam splitter, another on the other side, and then all results are conditioned to detectors in one side and the other simultaneously. and then you can get a violation of Bell inequality. You see, in our best situation was around 2.6. But you see, it depends on how you filter, how you do the various different filters here. If you use the full spectrum without any filtering, you barely, you don't violate, okay? You get just the limit for the inequality. It just means that your broadband spectrum, you probably have a multi-mode system. When you filter, you get something that's closer to monomode. And so what we can do is also that we can actually couple this kind of source into the network. So this is just the hack with the many fibers, and then you can send the photon in one of the sites and then get it back, and then go to another detector. And then you can see, for example, the R violation, the constitutive R violation as a function of the propagation distance inside the network. So we still didn't synchronize the clocks in different sites, but we can do this. We can just send the photon and get it back. And then we can already see how the correlations go down with the number of kilometers. Look, this photon is 818 nanometers. The fibers in the network is telecom fibers. Just for you to have in mind, the length for 3 dB attenuation for in 800 nanometers is 1 kilometer, okay? So it's completely different of using a photon in telecom. In telecom, it's 30 kilometers to lose 3 dB. So 4.5 kilometers is a lot. That's why the correlation function goes down fast. This is exponential, okay? But even with a few kilometers, we still have quantum correlations to play with. And I'm calling this attention because actually, oh, sorry, there is another thing for the SPDC source. So as I mentioned, we are looking for something that's simple, it's something that we can reproduce and distribute in the network. So actually, this ended up being an innovation project. We built a startup, that's QWeb, and this is the first quantum technology startup of UFPE, you know, and it's incubated in my lab. You know? And our goal is to have something that has a high repetition rate, around at least 400 kilohertz for the per generation rate. So we are going to use longer crystals, and we're going to optimize that recipe. And we had already some project that was approved for the company. And with this project, we were able to hire engineers and mechanical designers and physicists. And we got some drawing, and that's what we are fabricating now. And we're going to test, I hope, in the next 1 or 2 months to see if it's working. But the idea, actually, is to have something that is we can just turn on and have the photons, because this is something that we need to distribute in the network, okay? So we need to build many copies. Of course, in the beginning, we're going to have a prototype, and in the next site is going to be the second prototype, okay? And then the third site will be the third prototype. But eventually, we will reach a recipe that's going to be more reproducible. But we have to adapt our strategy, because for our project, we just have 1/3. Now is moving maybe for 1/2.5, maybe. So it was a bit more, it was liberated a little more funds. And we didn't have enough funds to really follow the original project. And the way we move around, we made some lemonade here with the lemons. And the way we move around is just, since we have a small network, actually can work with these photons at 800 nanometers. That's what I just showed, that, okay, they have a lot of attenuation, but they survive. The whole size of our network is like 10 kilometers. So we hope you get from one end to the other, but the photon will not be able to come back, okay? So this process that we are just sending and receiving back as just smaller distance. This was done before. We are not inventing this. So you can find this work here in 1996, okay, where they show how to do quantum key distribution with photons at 830 nanometers in a system with telecom fibers. It's not trivial, okay, but it's doable, okay? And that's what we are trying to do. Huh? And so we need to do many different things. Like, for example, for the polarization control is much harder. So any polarization problem that you have at telecom in 800 nanometers will be much worse, because that absorption length of 1 kilometer is also connected with the dispersion in 800 nanometers. So the dispersion in 800 nanometers is much larger than at telecom. So all problems that you have with polarizations to control in optical fibers, it's like we are work with 100 or 200 kilometers telecom fibers, okay? But there is a way, there are ways around, and there are ways to really be able to control this. And one of the tricks that we learned is, for example, when we put some light into a telecom fiber, but the light is at 800 or 780 nanometers, actually we include a single mode fiber at 800 nanometers, and then we put the light from single mode fiber in 800 nanometers to single mode fiber in 1500, and then we do our hide here inside the fiber, and the output, we also put a fiber with 800 nanometers, and then it goes to an analyzer. And then you get something like this. So this is exactly this protocol with a path length inside the network of around 1.4 kilometers. And then we set up this polarization to be close to vertical here in orange, and then we measure the two outputs. And this horizontal scale is 20 hours, okay? And so you see that actually, this is passive, so there is no active stabilization of polarization. And for us, at least, it was impressive that we could get really, it really fluctuates, but it comes back to the vertical. You see here, this experiment starts at night, and this is just daytime. So this huge fluctuation, but it always goes back to have some nice polarization. So we are really hopeful that with some active stabilization that we need to do anyway, we are going to be able to work with this kind of system. That's what we are doing now, to try to see if we can get really correlations in polarizations with this kind of protocol. I mean, but it's really critical, these single mode fibers. If you don't do it, then what happens is that you end up having some mode strange thing here that you really need to clean up with the single mode fibers in the end. So this is really very recent results. Okay. So this is just a quantum random number generator that's already working. This is an example of something that's relatively simple. You can buy it, okay? You can buy from different companies with different characterizations, something that's more sophisticated. It can give you much faster keys, and you can buy something that's cheaper but slower. But in the end, for an academic network, it's quite interesting to make, because what you have here is just a diode laser, and then you have some homodyne detection here. So you are measuring actually shot noise, okay? And the shot noise gives you some noise, okay? And this noise actually feeds an FPGA system, and from that noise, then you generate your random key. And the thing is, these different elements, like the homodyne detection, is something that's based for quantum optics. But actually, if you get a noise, and then you want to generate a random key, that's also basic for signal processing. So if you are an engineering student, like this is an engineering student, you see that in your classes, your regular classes. So that's a very good exercise that you can put together things that are more or less easy for one field and the other, and then when you combine, then the students get to learn a lot. We don't know if we're going to develop a small circuit to do our own random number generator, or we are going to start buying it. We don't know. But it's really important to do it, and the students use all this knowledge that they learn from different aspects. And so let's move back here. I still have some time then. So you see that this network, I come that we have this team here, we have this team here and here, but there is another site that's being set up. That's the Quanta. This is a fourth node in the network that we also have money to build it, but we are going to start it. And that's an Institute for Quantum Technology at UFPE. And so this is actually a FinApp thematic center. It's a FinApp project. And it's a very peculiar story, because what happened here is that, so we have many professors that work with quantum information, quantum technology, both like in quantum memories, quantum optics, theory, and associated with our postgraduate program, if it's a level 7 program. But the thing is that we also have a group in the electronic and systems engineering. That's what I just showed you, that the group that collaborates in the quantum networks with us, and they have a lot of experience in these different schemes, for example, to do optical networks or post-quantum cryptography. And you have also, but we also had a group in production engineering that was specialized in machine learning and an optimization production process already using quantum computation, okay? And you see that you have these graduate programs that are all, I mean, well evaluated, both in informatics, production engineering, the electronics, and physics. For electronics, we also had a quantum computation group, an artificial intelligence group, and communication systems group. So we have all these groups, and all have different projects related with quantum technology. So we have a project on quantum internet with atomic systems. We have this project with the telecommunication groups in multiplexed quantum communication systems. But the production engineer had a project of exploring quantum technologies for safety, risk, and reliability engineering. Okay? So it's really an optimization, very applied group. And the informatics center with physics had also a project on optimization noise quantum device of intermediate scales. So actually, at a certain point, we decided to just start to work together and then build this institute. And just to call your attention, like we had just the first general meeting in August, I mean, 2 months ago. And this is just the management committee for the institute. And it's interesting to see, these are all the people that was present there in the first meeting. These are professors, doctors, I mean postdocs. These are doctorate students, master students, and this is undergraduate students. And they are all already engaged in different groups working in different aspects of quantum technology. Well, we have management committee. This is just the periodic groups here. You have the quantum network I just presented. We also have, you see photonics and chemistry, that's a different group that we work. Theoretical quantum information. This is a group in the informatics department. Software for quantum devices. This for the production engineering, the machine learning, post-quantum. So we had already a lot of activity even previous to the institute, but now that we are starting to put together, that's the first meeting, so we have already a certain critical mass to work with. And one of the things that we are going to just reform a space that we have there in this big building that's on the side of the university. That's the site that was there in the map, okay? So in the fifth floor, so this is an empty building nowadays, okay? This was an old Sudani agency was, and the university is now reforming everything and transforming in a technological, infrastructure in general. So now the administration of the university is here in the last floor, and everything's empty, and then we are start to build things now. But in this project, so now these floors are all like this, everything's empty. So we should have just some infrastructure, auditorium, and I just want to move forward to, so we have a theoretical quantum computing lab. Many of the groups there are theoretical groups, and we have this photonics quantum computing lab and a quantum communication lab. So this quantum communication lab, that's where the link to the received quantum network will be installed. But I think it's also interesting, our photonic quantum computer that we are planning to buy inside this project. It's very good that Stephen already introduced this kind of system. The idea here actually is just we are going to provide the university this quantum light source, and I will discuss the options for that. But we are buying a photonics circuit, exactly like Stephen described, and we are going to buy also a single photon detector bus. Yeah. For us, it's really interesting to have this modular structure because this can work as a computer, but this can also work connected to the quantum network. And that's the whole idea. We can explore both quantum computation protocols, but we can also explore quantum communication protocols that are more sophisticated. And just to call attention for this light source, so the first option is the magnetic optical traps, because then you can have single photons and can have synchronized single photons. And the idea is to combine with some fiber arrays, okay? We have already these 7 independent photonic channels, some fiber arrays with 7 independent photonic channels. This is actually a subject of some that we are trying to collaborate, even Stephen, with the multi-core fibers, for example. That would be also in addition to this kind of system. If these were multi-core fibers, then we can actually use them to connect. This fiber array means that they are just a bundle of fiber together, and then they separate to 7 different fibers, single-mode fibers. But we can do other stuff. And the other thing is that we have some prototypes for the magnetic optical traps that are more plug-and-play in the sense that we have some, now a specific project to develop atomic traps that are more, user-friendly. And so that's the idea. Now we have a team from different, from both of physics department, so informatics and engineering, that we are actually, we are responsible for building a machine to be installed at the quantum. And also that company that I mentioned, we are also using the engineers to try to develop a more robust magnetic optical trap. And the second light source I already presented. That's just this photon pair source. Probably this is going to be the first one to be used because we have a high repetition rate, and then you have a lot of stuff that you can do with a single photon. Stephen already mentioned it's not trivial to define how to do quantum computation in this kind of system. You can always think, okay, 2 modes is 1 qubit, but that's not actually the best option. Sometimes you can find, for example, a 2 qubit protocol, and then there is a way to do that with 1 qubit. And then you do the coding in 1 qubit, and it gets much more efficient. And so it's really tricky. We had actually a whole group set up from that group that I said that we periodically meeting. It's just photonics and chemistry. It's just to see how can we work with chemistry protocols using that kind of generic photonic circuit. And that's what we've been learning. It's everything but trivial, okay? But we had already a list of experiments that we want to do as soon as we receive the system. And we can certainly start with 1 or 2 photons. 1 or 2 photons will be able to do a lot of stuff. And then this will give us time to build more photons in the trap, in the atomic trap. But actually, we also want to go to the different, a third option, which is nanometers, deterministic nanometers. And that's a collaboration between, the group in quantum optics and also Anderson Amaral, that he works with nitrogen vacancy defects in nanodiamonds. This is a measurement from his lab here. You have a nanodiamond, and then you measure the G2 function from the diamond, and then you can see that it's really a single photon emission. And so he will work in associate with Eduardo Padron. Eduardo Padron, he works with the lithographic lab there, so he works a lot of material science systems. And so he's very invested in this project now. And the idea is then to get this nitrogen vacancy materials or some 2D material and start to build cavities around, see if we can control. As I mentioned, we have this other photon source that we can start to work, and we have time to develop this. So the time we'll have a lot of work to do before, but as soon as this becomes more functional, the tendency, I would say, in the future would be for this to be one of the most important systems, or the most important system here. And so finally, the other parts of the circuit, the photon circuit we are going to buy, Stephen already mentioned, there are at least 2 companies that sell this kind of systems. It's amazing, actually, because a couple of years ago, these are things that people do in the lab but not exactly sell, but they turn into commercial systems, and it was quite nice for this company. They were okay to sell us this system in 700, 800 nanometers, exactly the wavelength compatible with our rubidium atoms. and this is a 20-mode processor. And from quantum optos, we are getting this is a buffer with 32 SNSPD detectors. And as I mentioned, we have already many applications in mind. We have already some applications in chemistry, and also optimization algorithms, because we have the theoretical groups both for production engineering and the informatics department. When we decided to move in this direction, it was not just a decision of the physics group. It was actually a project that would interest also the computer science groups, because they were interested, they didn't care to have like a very large computer. They said, okay, we can have a small computer, but we want to participate in the process to build a computer from scratch from the basic elements. And then that's what we are going to get, because we are going to be probably one of the first clients of this company, and we are going to get we are going to give to the processor just like a transfer function. It's something like below basic, but there are some software that is built already. For example, for Candela. Candela has some language that you can use to actually simulate this kind of processor. But again, this language is still below basic, okay? Below basic, I mean, not basic, assembly, okay? And so it's really very close to the machine, but the informatics department is exactly interested in this, because what they don't like nowadays is that if you want to use, for example, an IBM computers, which is interesting because you can try to get some quantum advantage from it, but actually, you have to do a program that's very specific to the machine. But it's the machine that you don't control. So the professors there in the computer science group, sometimes they do an article on just how you can initialize a function in an IBM computer, okay? But this is valid only for that present configuration of the IBM computer. That configuration changes over time, they don't necessarily inform the users. So it's a very strange situation, especially for the people that work on software. Okay, physicists, for us, find that great. It's finally working. Okay, but then for the people in computer science, they look at, okay, it works more or less, and then you have this problem to initialize the system, and then you have to pay to solve the problem of the company. Okay, so they mentioned, okay, if you can build a computer with just a couple of qubits, it would be interest for us. We would like very much to build from scratch. And so now we already have some people from chemistry, but now the people from computer science are also getting involved. And exactly in the optimization algorithms. Once we get optimization algorithms, then you can also get on board the people from production engineering. So what's the idea that is getting more interesting now is that from this network, actually what we are adding here is a quantum processor, and we are going to operate this network initially exactly at 800 nanometers, and we are adding a processor in 800 nanometers. So actually we have a small quantum network integrated with a photonic quantum computer. So we have a small quantum internet that we can call that, okay? Because we're going to have some sites that we can really distribute in quantum entanglement, and we are going to be able to do some processing in the sites. So it's just a very preliminary quantum internet, but it's something that we can start to build something more sophisticated. And one of the things that we want to apply besides all quantum computation applications is to actually more sophisticated quantum communication protocols. So the DLCZ protocol is something that's really just, as I mentioned, it's just one of the first protocols, not the most efficient one. And actually to investigate these more sophisticated protocols, this 20-mode processor also has a good size. Okay, we can really work with, for example, process using cluster states, for example. And then we can look for quantum advantage, not in efficiency, but in safety, in maximum distances, and so in other aspects. And for example, this article is from 2015. It's a proposal for an all-photonic quantum repeaters, which use this kind of cluster states. And the thing is that for this kind of application, you're going to use a more complex state, so you have different, it's a higher number of photons or at least modes, but it's not very high. I mean, with already maybe less than 10 modes, you can already do something quite interesting, okay? And so that's kind of processor may allow us to enter in this kind of problem. And finally, so if we have more funds, okay, then we can move to telecommunication applications. So the idea is we have already the RNP network that makes a circle around Recife. So now we are connecting UFPE with UFRPE. That's just 10 kilometers. But also, this whole circle here, up from here to here, is around 30 kilometers. So the whole circle is around 40 kilometers. So it's a good distance to work with telecom. And particularly interested is to connect with CSAIR. CSAIR is an innovation center, and it is also like an Ember-peer reference center for cybersecurity, okay? And so we want to really connect with them at a certain point. Now it's just other stuff that's going on. So we are also entering some quantum sensing. This is not connected to the network yet. It's just to mention that this is another thing that we are entering into is this idea of a quantum sensor using LIDAR. So it's a LIDAR quantum sensor just to characterize gas samples. I think Irina Novikova mentioned one of the possible quantum sensing technologies was exactly quantum LIDAR, and that's what we are entering now in Recife. And also another thing to call attention, so of course, we have many people working the network, but a lot of work is done in the lab that I'm coordinating, the Laboratory for Quantum Networks. So this is the present team of the laboratory, both for professors, postdocs, and doctorate students, masters, and a lot of undergrads. So we have a lot of, really, the students are the ones that are really driving the lab nowadays. As I mentioned to some people here in the conferences, I mean, we see that they're really interested in the field, not only physics students, but also electronics engineering, computer science, and so it is a different mix of students, I would say, nowadays. But they are very interested in the field and excited. And of course, we have funding to do all of this. And finally, okay, just to end, so we are building this initiative at UFPE that's still a little bit under the radar. We don't have a website, okay? We don't have anything. But we do have different projects, and we are really working together. So we have in quantum communication, I described here in more detail, the Recife Quantum Network. I just discussed the innovation connected with the QWeb, which is more hardware. I didn't discuss our collaboration with Dobslit, for example, for the companies. But for quantum computation, I described this thematic center that we are building, but I didn't describe, for example, there is an INCT for applied quantum computation that is coordinated by the computer science center there in Recife. And we have, there is a collaboration with Itaú Bank and all of the same companies here. And now we have this quantum sensing as well with this quantum LIDAR initiative that is a project with Petrobras. So we are starting to build, I think, a more consistent quantum technology initiative there that's quite broad. No? Even though it's also very academic, so that's why it's broad. Sometimes when I go to the meetings that are more to innovation community, they always ask, but you're doing everything, you cannot do everything well. I say, okay, but this is an academic initiative. I mean, we are not aiming only at innovation. Innovation is something that we are certainly interested in, but we are forming students, and we are doing research. And I mean, if you are forming students, for example, to know 3 different techniques for quantum cryptography, that would be much more interested if we're just focusing one technique, for example. No? The same goes for quantum computation. We are going to do photons quantum computation, but the students, they're still going to do other kinds of computation. They're still going to access IBM quantum computers, D-Wave if possible. I mean, it's important actually to have the idea that you can do quantum computation with different platforms, okay? And so that's why it's broad, but it's also, we find it interesting this way. So thank you for your attention, and we can discuss more now.
So Daniel, you can do like, with the photonic quantum computer and the network, you could do like blind quantum computing where you actually send qubits to the computer, send them back to the sender, things like this, like actual real, say, advanced next level quantum communication, or distributed quantum computation and things like this, yeah?
Yeah, I hope to do distributed quantum computation. If this way specifically, I hope so, but I would be interested to see what this would be. Because actually, I mean, what we are looking for now, because, I mean, there are many things that we can do, but we need to focus on a couple of things. And, I mean, I would be very interested to have more ideas to do, because I didn't mention, but that detector there, it comes with a 2-year, I mean, validity, like we have to do a lot of maintenance every 2 years. So we have to work a lot with it. And in 2 years, we have to do some maintenance, and then we really have to program the work. But for example, there are, for the quantum networks, not exactly with the computer, for example. We have ideas to do a tripartite systems. And for this, we need a symmetrical network, for example. But distributed quantum computers, for sure, is on the line. And we are going to have 2 sites with material systems also. We're going to have both the quantum computers and quanta, but we're also going to have the quantum networks laboratory. So we can also do some storage if needed. You know? But I'm interested, we need to talk about the different ideas to do.
Any other question?
Okay, so,
Okay.
okay, so thank you.